we will continue with the topic of HPLC because it is most important analytical tool that is being widely used both for biomolecules, that means peptides or proteins, or for even small molecules like acids, alcohols and small esters and so on. Actually that is why we would like to spend more time on the concept of HPLC, and there is a relationship between this HPLC which is used for analytical purposes vis-a-vis the normal separation techniques using chromatography, different types of chromatographies which we looked at. So HPLC, the piece can be for performance or it can be pressure, because it is a very high performance system, as well as the pressures are very high, the back pressures are very high because the tube diameter is small, particle sizes are in micron range, so the back pressure developed is extremely large, and so you need very high pressure pumps to operate in an HPLC. So it is for identifying an unknown compound, as well as it can be used for quantifying an compound as well actually. Okay, so that is the main advantage of HPLC, we can use it for both the purposes. There are two types of HPLCs, I talked about it in the previous class. One is called the normal phase, that means you have a stationary phase which is polar like a silica, and you have a non-polar solvent. Non-polar solvent means it could be hexane or any other hydrocarbon. The other type of HPLC is called the reverse phase HPLC, that means you have a non-polar stationary phase and a polar solvent. So non-polar stationary phase could be a long chain hydrocarbon, and the polar solvent could be water, methanol, acetonitrile and so on. So nowadays the fashion is to go towards reverse phase because the solvent which you are using is extremely cheap. Mostly you will be using water, predominantly water, and it could be some other organic polar compound. So in HPLC we consume quite a lot of solvent, both for analytical purposes as well as for regeneration and cleaning, flushing and so on. So reverse phase HPLC has become extremely popular. Now a typical setup, I talked about it in the previous class, you have a reservoir for the mobile phases, and then we have the pump. It could be two types of approaches, one is the isocratic or other is the gradient. In an isocratic we are using only one solvent, so generally you will require only one pump, whereas in a gradient system we may be using two or more solvents. You are changing the solvent, that means you are changing the dipole moment so that the separations get enhanced or improved. So you have the pump or pumps, and then we have the injector where you are injecting your solute mixture, and then the column, this could be several feet, and then finally the detector. There are different types of detectors, and that is what we are going to spend today on, predominantly the types of detectors, their advantages, disadvantages and so on. So this is a typical HPLC instrument. We sometimes also have a guard column here. The guard column helps as a filter unit. It captures small particles, it captures some polymeric waxy material so that it prolongs the life of the main column. So that is the main advantage of using a guard column, and once it gets used up we can throw the guard column and we can replace it with another guard column. Okay, so like that we can do, that way the life of the column is prolonged. Now typically when I inject a sample, after some time I am going to get a chromatogram like this. The peak is going to rise, reach a maximum and then fall down. So this is called the retention time, that is the time it takes for the maximum of the peak to appear. Okay, so the x axis here is time and you have the detector response here. So this maximum time is called the retention time. Okay, you can also use it as retention volume, that means volume of the continuous phase we collect until the peak reaches the maximum. Now if you draw two tangents at this inflection point, and if you measure the width at the base, that is called the W, width at the base, and we can also have something called half width at the maximum. That means if this is the maximum height of the peak, half the maximum is this, so the width measured here is called width at half maximum. Why do we need all this? We can calculate a term called theoretical plates. Theoretical plates tell you the efficiency of the column. More the number of theoretical plates, more is the efficiency. So if I am comparing two columns, and if one column has higher number of theoretical plates, then we can say that column is more efficient than the other column, all other things being the same. So if we measure W, that is width at the base based on this tangent method, or if we measure width at half the maximum, then we can use either one of them to calculate the number of theoretical plates. So if you are using width at the base, then the formula is n is equal to 16 Tr by W whole square. Tr is your retention time. If you are using width at half maximum, then we use n equal to 5.54 Tr by W half whole square. So this is a very important formula for measuring the number of theoretical plates or number of theoretical stages. Okay. When you are doing HPLC, and if this solute mixture contains several components, life is not going to be very simple that you will get individual peaks well separated out, but it is going to be very problematic. Say for example, it may be like this, you get very good peaks for component 1, 2, after some time you get the component 3 and 4, but component 5 and 6 is coming very late and it is very broad. So we will not be able to accurately measure component 5 and 6 concentration, and it is happening after a very long time, because as you know the base x axis is time. So you are extending unnecessarily your analysis time. So I can try to bring it closer, that means I can reduce the retention time of the component 5 and 6, okay, by changing some conditions like changing the solvent system or changing the ratio of the solvent. Then what happens? 5 and 6 is coming okay, but 3 and 4 has merged, we can see them hardly, but 1 and 2 completely merged, that you cannot differentiate 1 and 2. So again this is also not desired. Okay. Then if we keep playing around with the solvent systems and ratios and so on, you may be able to separate out 3 and 4, but 1 and 2 is not separated. So we are closer, but not really the good or the best set of chromatograms. So we have to again play around with this set of conditions so that 1 and 2 also get separated. So if we want to measure accurately the concentrations of 1 and 2, even this is not good. Okay, so we may have to improve further so that we get a good separation for 1 and 2, but at the same time 5 and 6 do not go very far away during the analysis time. So you see that if you have a multiple components in your mixture, it is going to be a real challenge. You may have to optimize the conditions until you get the best set of results where all the components in the mixture which you are interested in get well separated out at the base. That is very important. That is called at the base, because here they are not separated out at the base, neither here. Okay. Now when you are using a normal phase chromatography and when you are using reverse phase chromatography, both of them operate in different principles. So we need to see how to improve this type of separations. For example, if they are very close, you are using a normal phase chromatography, A, B, C are very close and you want to separate them. Okay. So suppose you are operating at medium polarity, what do? You switch over to low polarity. Low polarity means you make it more hydrocarbon, that means you make it more hydrophobic, then you get a good separations of these peaks. Why is it so? You have the normal phase which is the polar, so it attracts more hydrophilic groups, it does not interact with the hydrophobic groups. Okay. So by going down in the hydrophilicity, by making it more hydrophobic, we are getting a good separations. Now let us go to reverse phase chromatography where the stationary phase is a hydrophobic material like a C18 type of material. Okay. So now if the peaks are very close, what do? You change the polarity to high, from medium you go to high. So when you go to high polarity, that means components, polar components are retained in the solvent, so the separations are much better. So if you are using a normal phase chromatography, if you want to achieve better baseline separation, you move to low polarity. If you are in reverse phase chromatography, if you want to achieve good baseline separation, you go to high polarity solvent. So you see the approaches which you adapt depends upon the type of chromatography which you are using. Okay. Other factors which affect your column efficiency: the velocity of the mobile phase, the diffusion coefficient of the solute in the mobile phase, diffusion coefficient in the stationary phase, that means how the solute gets diffused inside the pores of your stationary phase, the retention factor, the diameter of the particles. Smaller the diameter, better is the separation, but then the back pressure is very high. Thickness of the liquid coating on the stationary phase. As you know, we have the stationary phase is a solid, the mobile phase is a liquid. When there is a two phase system, you are always going to have a liquid layer which is settled on the solid, and your solute has to diffuse through that if it has to reach the solid phase. So there is a mass transfer resistance for the liquid solute to move from the bulk of the liquid phase to the solid surface. So smaller the thickness, the resistance is less. Higher is the thickness, then the resistance is more, and the solute will take much longer time to diffuse from the bulk and come down to the surface of the solid. So what are the factors that affect? The factors that may be affecting this liquid thickness may be density of your continuous phase, viscosity of the continuous phase, the size of the stationary phase material, the turbulence that is happening inside, the voidage or the void space inside the column, your distribution of particle size. So many factors affect that. Okay. Now let us look at detectors in HPLC. As I said, detectors play a very important role, and there are different types of detectors depending upon the application which you are looking at. Okay. The most simple one which I mentioned last time also is the single beam UV visible. Okay. So you have a cuvette where you take in your solution and a UV visible instrument and you measure the lambda maximum. So generally in a UV visible you detect at 254 nanometers, that is the default wavelength, but we will be able to set it to different wavelengths, but you can measure only at one single wavelength, but it is extremely cheap. If such an instrument you have, it is very cost effective. We can use different filters to look at different wavelengths also. It is a non-destructive test, that means after you have done the experiment we can collect your sample and use it for some other analysis. That is the main advantage of this type of detector, because as you know, if the quantity of the solute is really scarce, you will not be having enough of these solute for performing large variety of analytical measurements. So in that case we do this HPLC, collect all the sample, again take it back, maybe perform some other analytical tool. So that is the main advantage actually. But the disadvantage, not all compounds will absorb light, so that is going to be a problem. Okay, next one is diode array detector. Okay, it's also a very common tool used in HPLC, and it's quite versatile, and we can measure it at several wavelengths because the diode array detector scans at a complete range of wavelengths every second. So the amount of data you collect is large, and this is very ideal for R&D type of purposes. So initially I will not know what will be the lambda max of the compound which I am going to separate out. So in that case I use a diode array detector. I will scan the entire wavelength, and from that I will know what will be the lambda max of that compound. But the data you are going to get for each second, if it is going to scan the entire wavelength, is huge volumes of data actually. That is the main disadvantage, but it is ideal for research purposes. So single beam is ideal for routine quality control, whereas DAD is very good for R&D type of work. Again it is a non-destructive type of technique. That means after the experiment we can again collect the solute back and use it for some other analytical purposes. Next one is refractive index. So there is a change in the refractive index of the solute which is measured. This is again a non-destructive test, ideal if the solutes have different refractive indices, but then it is extremely temperature sensitive. So even a small change in temperature of the order of 0.001 degree can affect the refractive index, so you may start getting very spurious results. Okay. So that is why nobody uses it nowadays. A small change in the temperature is going to affect the RI, but it is used in online monitoring. So you are having a manufacturing plant and there is a product which is being produced, you want to know the concentration. So there you in the pipeline you put a RI detector and you calibrate the RI detector and then you start measuring the changes in RI, that will give you an indication of the changes in the concentration. So it is ideal for online and it is extremely cheap. That is the main advantage of using a RI type of detector. Okay. Now another detector that is called evaporative light scattering detector, ELSD. This is also used nowadays, but the main disadvantage is it is a destructive technique. That means after you have done the measurements or analysis, the product is not available for some other analytical tool. It is very useful for large molecules and it is linear over a wider range. The analytes are desolvated in the detector, okay, the solvent gets evaporated, the reduction in the light intensity is detected, okay, due to the scattering by the analyte. So that is why, as the name implies, it is a light scattering. So the light, the laser falls on the analyte or the solute and it gets scattered, which is measured. Okay. So larger molecules or more concentrated the molecule is, the scattering is also going to be more, which is a measure of the size or the concentration of the molecule. So the scattering is measured and hence the size or the concentration of the molecule is implied. That is it is a very good technique and it is quite accurate on that. Then we have the mass spec detectors. MS means mass spec. Nowadays mass spectrometry detectors have become very useful. It can give you a mass value for the solute or analyte. So nowadays LC-MS, that means liquid chromatography and mass spec are getting coupled together, and you can use the LC part for separations of the various solutes or biomolecules or proteins, and then MS can tell you what is the mass number of each one of the peak. So it is a combination of both the liquid chromatography and the mass analysis, and it is extremely useful because we can even look at the fragmentation of the mass, and from the fragmentation pattern we may be able to imply what is the type of biomolecule which is present. If the molecule is very small, organic molecule, it is very easy to detect or imply. If it is a large biomolecule, then it takes quite a lot of time to understand the structure, but there are many databases nowadays available which gives you the MS spectrum or MS fragmentation pattern and then try to imply what the molecule is. So HPLC per se vis-a-vis the LC-MS, that is liquid chromatography MS, there are slightly differences in these two. Okay. The LC part of the LC-MS is much smaller than the HPLC, in the sense the internal diameter is very small, the column is also very small, flow rate is also very less in the LC-MS, whereas in the HPLC the length of the column is very large, flow rate is also very large. See, for example, you may be using a 1 mm column for LC-MS work, whereas the HPLC may be a 4.6 mm column. You may be using very small capillary column, no, 300 micrometers or 75 micrometer capillary column, and you may even go down in flow rate even 100 nanoliters per minute, that is a very small flow rate. So such small miniaturized sizes can be used in LC part of the LC-MS, unlike the HPLC where you need to have higher flow rates, higher diameter, longer columns. Now how does the reverse phase chromatographies work? There are several mechanisms which has been proposed, and in real situation all these mechanisms are combined together, and that is how a real system works. The three mechanisms or theories which have been proposed for the reverse phase chromatography to work are, one is called the hydrophobic theory, other is called the partition theory, other is called the adsorption theory. So let us spend little bit time on each one of these theories. Okay. What is hydrophobic theory? So there are cavities in solvent created by hydrophobic portion of the analyte molecules. Okay, so there are cavities which are created because of the so there are hydrophobic portion, surface tensions are there. So there are interaction of polar functions in the molecule with the solvent. Okay, so stationary phase is passive. So in the hydrophobic theory, stationary phase is very passive. So we have the solvent and the analyte interacting because of the cavities of hydrophobic regions. That is what the hydrophobic theory says. Now partition theory, this is the partition which we know we have been looking, we have been talking about in liquid chromatographies or in extractions and so on. So the analyte distributes itself between the aqueous mobile phase and the organic stationary phase. Okay, so there is a partition. Now there is the retention of these analytes in the column is correlated to the log P. Log P is nothing but logarithm of the partition of an analyte between octanol and water. Octanol is considered to be hydrophobic and water is considered to be hydrophilic. So more hydrophobic a molecule, it will be found more in octanol than in water. So log P will be large. More hydrophilic the molecule is, it will partition more in the water layer. So the log P will be smaller. So smaller the log P, you can say the molecules are hydrophilic. Larger the log P, we can say the molecules are hydrophobic. So there is a correlation between this log P and the retention. So if the log P is large, okay, so that means it is hydrophobic, then it gets stay put inside the column much longer. If the log P is small, that means the molecule is hydrophilic, so it comes out faster. Then you have the organic phase is attached on one end and it does not explain shape selectivity effect. So that means this theory does not tell you why the selectivity happens because of shape. Okay, so molecular shape does not come into the picture, it just considers the hydrophobicity of the molecule, nothing else. It does not bring in the shape factor. Whereas if you look at the previous theory of hydrophobic, there are pockets created in the solvent depending upon your analyte. So the shape effect comes into picture there. The third theory is the adsorption theory. So what happens, the analyte lands on the surface of the stationary phase, so it does not penetrate through. So there are a lot of non-polar interactions, that means hydrophobic interaction between analyte, hydrophobic portion and the bonded phase. Like bonded phase means you may be having a C18 or a C8 or C3, different types of hydrocarbons bonded to the solid polymeric matrix. So there is a non-polar interaction between the hydrophobic portion of the analyte and the bonded phase. So these interactions could be dipole, dipole, dipole induced dipole, induced dipole, induced dipole and so on. So all the forces, weak interactive forces are operating on this. So you see three different theories. One talks about how the analyte affects the solvent that is present and the stationary phase does not come into picture. The second theory is partition, that means the liquid in the stationary phase and the solute in the mobile phase partitions based on log P. The third theory is the adsorption, where the analyte lands because of non-polar interactions, hydrophobic interactions between the analyte hydrophobic region and the bonded phase. So these are the three different theories which have been proposed to explain the reverse phase chromatography, and in reality there could be combinations of all these three theories. Okay. So none of these can completely explain all of the observed retention in reverse phase HPLC. So it is a combination of all these three actually. So what are the parameters that are very important in reverse phase? The solvent strength, okay, that is solvent is the mobile phase. Choice of solvent, what solvent do I take? Do I take just water, do I take water methanol, do I take acetonitrile, do I take THF, do I take combinations of that, the pH of the mobile phase, and then silanol activity, okay. We will talk about this silanol activity as we go along because you have a lot of SiOH molecules which really creates a lot of unwanted interactions, okay. Solvent strength, water is a very weak solvent, so as you keep increased organic then there is a decreased retention, okay. Organic must be miscible with water, that means whatever organic molecule solvent you select it should be miscible with water. So if we keep increasing the organic content then the retention keeps going down because it is becoming, okay, it is changing the hydrophobic nature of the continuous phase. So for example I take 75% methanol, 25% water, so the peaks are very close, so it is a fast. Now I am reducing the methanol amount and increasing the water amount, you see at 50% methanol, 50% water, slowest separations are very high, okay. Why? I have brought in more water, so that means I have made it more hydrophilic, so the separations are much higher, whereas here I am reducing the water content, that means I am reducing the hydrophilicity. pH, pH generally affects ionizable compounds, okay, like organic acids, organic bases and so on, but then we have to suppress the ionization as much as possible in a reverse phase, because once it gets ionized, as you know ionized molecules are highly polar, so they all the ionized molecules will club together and you will not get a good separation of those polar molecules because ionized molecules are extremely polar. So we have to change the pH so that this pH is suppressed. Once you do that then the hydrophobic nature of the stationary phase come into picture and the separations of relatively different polar compounds are enhanced. So we need to have very good pH control, that is very important if you are looking at ionizable compounds like organic acids, bases and all that. So we can use buffers to control, so 0.1 pH unit significant effect on retention, so such a small amount it will definitely affect your retention. So buffer mobile phase for pH reproducibility we need to do. So pH of the buffer should be within 1 pH unit of pKa of the acid, okay. So pH should be equal to pKa for acids. So we can say buffers are very weak if you are using 100 millimolar or less than that, but then most important thing we need to see whether these buffers are soluble in your continuous phase, that is also very important actually, okay. So for acids you adjust the pH so that it is equal to the pKa of the acid. So what are the common buffers we use? We use phosphate, we use acetate, we use citrate, okay, but then phosphate we can work at pKa 2 or 7, acetate at 4.75, citrate at 3.08 or 4.77 or 6.4 pKa values. Ideally you should buffer between 2 to 8, okay, more on the acidic side, so 2 to 8 so that you use your buffers so that you are able to keep your pH within that range. Silanol activity, so reverse phase ligands occupy about 50% of the silanols, that means there are silica on your stationary phase and then you put in your long chain hydrocarbon to make the surface hydrophobic. The long chain hydrocarbon could be C18 or C8 or C3 or something, but you are not going to replace all the silica SiOH which is extremely acidic, okay. So if you are replacing only 50% then the remaining 50% is there which is going to create a lot of issues. So they are active, they are weak acids, okay. So there are different types of silanols, surface will be highly non-homogeneous. So the silica, if this silica next to each other form a bridge like this, then this is an inert siloxane bridge, but normally you will be like this, SiO, there is a negative charge here, small positive charge here. So this is going to create problem because there is a small positive charge here. Another problem, it can form this type of bonds, that is the two adjacent silanols, and H plus can get released, then you are in big trouble because you have protons in the continuous phase and you have negative charge on the surface of your stationary phase. These are called hot spots. So if you have solutes which are also having certain charges, then there is going to be not a hydrophobic interaction, but it is going to be more of ionic interaction, then you have completely destroyed the hydrophobic chromatography principle. So different types of silanols, and the surface will be highly non-homogeneous. Ideally I would like to have this situation, but then many of the time you will have like this, but then if you have like this you are in big problem because protons are liberated, and you are going to have O minus on the stationary phase. So you need to understand this and see whether I can neutralize these passivating or neutralization, that is what is called, before you actually perform your HPLC studies. So what does silanols do? They cause peak tailing and excessive retention because you have sometimes O minus, you have charge, so your molecules solutes get captured and slowly get released. So we can end cap these molecules using a smaller group. Pre-treatment of silica, that means we can fully hydroxylate it, or we can use very high purity, that is the best actually, fully hydroxylated or high purity material, or we can end cap it by having a small molecule. So this is how you can get rid of it. So if you are in having a peak tailing or excessive retention, you know this is a silanol problem. So what does silanol do? It interacts through hydrogen bonding, it creates dipole-dipole interactions, it creates ion exchange because you have O minus on the surface and you have H plus which is floating around in your continuous phase. Low pH silanols will get protonated, or we can add basic modifier like a tetraethyl ammonium to compete for the sites. Okay, so you have O minus, then we can add some basic material like tetraethyl ammonium plus type of thing, which will go and block those silanols. Now how can you use the HPLC for detecting a compound in the mixture? Suppose we know what the compound might be, okay. So we know that possibly we are producing a fatty acid ester. So what do? We get an authentic pure compound of the fatty acid ester and then we inject into the HPLC and note down the retention time. And when you inject your mixture at the same conditions, and if you find a peak at that particular retention time, you can be sure that the unknown peak in the mixture could be this particular fatty acid ester. You can also do something called spiking. So what you do is you take this pure compound, add little bit to the mixture and then again do a analysis, and if the peak height increases or the peak area increases, when after you spike it, then you can be very sure that that particular peak is the compound which you thought it was, okay. So that is called spiking, okay. So in a spiking what do? You first get a chromatogram of your mixture and then you add the pure compound, little bit of the pure compound in the mixture, and see whether the peak area or peak height goes up. If it goes up, then you can be sure that whatever the compound which you have added, the pure compound is that particular peak. So that is how you identify the presence of a compound. So if you have 2 or 3 compounds, you do the same thing for all those 2 or 3. You try to get you try to purchase these authentic components and then get their retention time, the pure component retention time, and then use that number to check whether peaks are appearing in your mixture. That is how you need to do a identification presence of a particular compound in a mixture. Okay, then how do you quantify that particular component in the mixture? What do? You prepare something called a standard graph. So what do? Now you know what is that particular compound in your mixture. So you take different concentrations of that compound, inject it into your HPLC and get the area under the curve. Then you plot a graph between the area under the curve and the concentration. Okay. So once you do that, you should get a good straight line. If you do not get a good straight line, then that means you are not operating in the linear range of the response of the HPLC. So maybe if you are using very large concentration differences, you will not get a linear response. So it is always good to operate in the linear range. So once you do different concentrations of the known compound and measure the area under the curve, you plot a graph between the area under the curve and the concentration, and you should get a straight line connecting these two. This is called a standard graph. So if you know the area under the curve for the compound in the mixture, using this standard graph we can read out what will be the concentration. This is how you need to do. So you inject your mixture, calculate the area under the curve for that particular component in the HPLC chromatogram, and then from this graph you tell what is the concentration of that component in the mixture. So if you have 2 or 3 components, then you prepare standard graphs for each one of the component, and then in the mixture when you inject, you get the areas of each of the component from the chromatogram of the mixture, and then you read out the concentration for each one of the component using different standard graphs. So this is how you measure or estimate the concentration of the component in your mixture. So HPLC is extremely powerful to do both these operations. It can tell you whether a particular compound is present, or it can also tell you how to determine the concentration of the component. Another method by which we can do is called the internal standard method. What do you do in an internal standard method? We add a known concentration of a particular new component which is not part of your mixture to this mixture, and then see what is the area under the curve of that particular component. So by looking at the ratio of the area under the curve of that internal standard with the unknown component, we can again measure or estimate what will be the concentration of your compound. So there we are using something called a standard. The standard is another compound whose concentration is known, which we are adding, and by measuring its area under the curve we know the response of that particular component, and we try to extrapolate it to the response of the compound which we are trying to quantify, and then get the concentration of that particular component. Okay, that is called the internal standard method. Okay. Another approach, as I explained, is the standard graph. These are the different ways by which you can tell what is the concentration of a particular compound in your mixture. Now in a HPLC the most important thing is the method validation, because when you are developing a method you need to validate it totally and completely, especially if you are working on clinical trials. The FDA, that is the Food and Drug Administration, is very particular that whatever methods you develop is completely validated, and the method validation protocols, the results, the analysis have to be put with the papers when you are applying to the Food and Drug Administration for coming up with a new method. So method validation is the process by which it is established by laboratory studies that the performance characteristics of the method meet the requirements for the intended analytical application. So it meets the requirements for the intended analytical application. That means if I am developing a method for measuring a particular metabolite in my mixture, at a concentration of 0.1 millimoles per liter, then the method which I develop should be accurate enough to measure that particular concentration. That is what is called the method validation. And as I said, in all drug testing laboratories, in all clinical trials, method validation plays a very important role. It is most important because the Food and Drug Administration, that is the FDA authorities, go through these methods which we have developed to see whether they are accurate, whether they are good enough, whether they are robust to perform the particular tasks for which you have developed the method for. Specificity is the ability to assess without any doubt the analyte in the presence of components which may be expected to be present. That means if you may have many components in your mixture, but without any doubt the instrument should be able to detect your component of interest. So the mixture may contain impurities, mixture may contain degradants, mixture may contain matrices and so on. So you may have many components, but you should without any doubt be able to. That means the analytical technique which you are developing should clearly show the component which you are trying to identify. Okay. Accuracy is the closeness of agreement between the value which is expected with the reference value and the value which you found. Okay. So you are using the instrument and you are coming up with certain concentration value for a component. How close is it with respect to what is expected or what is the reference? That is what is called accuracy. So when you develop a technique, the technique should be accurate enough within the tolerance which is allowed. No, it could be 0.1% differences or 0.01% differences depending upon the type of component you are trying to measure. That is what is called the accuracy. So above certain accuracy, the method which you have developed might not be good enough for the task for which it is intended for. Okay. Precision. So if I am measuring a particular component in a mixture, if I do it many times, how close or how the degree of scatter is, that is what is called precision. So if I do it 3 or 4 times, am I getting the same result or am I getting randomly different results far apart from each other? So if I am doing that, then I am in trouble because my method is not repeatable. Okay. So which is very dangerous. So each time I may get different answers. So precision tells you if I do it many times how close each one of these measurement is. So in precision you have two things, one is the repeatability, other is reproducibility. So in repeatability, if I am repeating it many times, how close they are. In reproducibility, if it is done in different labs, then how close the results are. Okay, that is called the reproducibility. And nowadays in clinical trials, as you know, drugs are tested in different parts of the world, different continents, different hospitals, and in each place they have measurements. They may use the same bioassay or analytical tool, they should get the same answers, otherwise they are in big trouble. Okay. So reproducibility is also very important. Repeatability is important because if I repeat the same assay 3 or 4 or 5 times, I should get almost the same answer. Then you have the intermediate precision, that means within laboratories variations on different days, different analysts, different equipment and so on, that is called the intermediate precision. So precision and accuracy, you can see both are very important. Precision is when I repeat many times, am I getting the same answer or am I getting a different answer. Accuracy is I get an answer, how close is it to the real answer or correct answer or expected answer, that is the accuracy. Detection limit is the lowest amount of analyte in a sample which can be detected, okay, by my instrument. So I may have 0.1 micromoles, can I detect that with my instrument, that is what is called the detection limit. But that is not necessarily the quantitation limit, because quantitation limit is exactly can I measure quantitatively the amount. Okay. Quantitation limit will be generally higher than the detection limit. Okay. I may be able to detect, there might be a small peak coming out in my chromatogram, but I will not be able to quantitatively tell how much it is. So quantitative limits will be slightly higher than the detection limit. Okay. So I need to know, when I develop a technique, can I quantitatively determine 1 microgram per ml of a particular impurity, because the FDA may be interested to know whether the technique is has a good quantitation limit, or is it 10 micrograms per ml concentrations that can be quantitatively determined. Then we have the linearity, as I talked about in the standard graphs. The response and the concentration of the solute should be linearly related, then only we can develop a linear regression relation between the concentration and the response. We do not like to operate in the non-linear range. So what is the linearity range? That is very important, and so if your concentration are very high, you may like to dilute it so that you operate within the linear range. So generally the analyte concentration versus the response, we would like to operate in the linear range, that is meant by as the linearity. Then range is the region that is the lowest and the uppermost concentration region in which I am operating, because none of the instrumental techniques or assays or the equipments can operate in the entire range of concentration. So they will always have certain range within which you can operate. So that range also has to be specified. Robustness is how stable is the technique even when there are small variations in your methods. Okay, I make a small mistake during preparation of the sample, or there are small mistakes in the solvent flow rate. So is the method very robust, or is it going to be changing dramatically when you have small mistakes incorporated? That is what is called robustness, and ideally we would like to have a robust technique, HPLC technique. So what are the method validation tools? We may have to use reagent blanks. That means if I am using solvents for extraction or dissolution, I need to test those also and see whether there are any peaks in my chromatogram coming out because of the reagents. Sample blanks, that means if I am using any matrices without my analyte, I need to perform an HPLC and see whether they are giving any peaks and whether those peaks are going to interfere with my solute. Test materials, that means we may take materials which are not real material, but they may be test materials. So these are the various method validation tools which we need to adapt to before we can tell the method which we have developed is good enough actually. So to conclude, we have spent a couple of lectures on the high performance and high pressure liquid chromatography. It is extremely powerful tool for identifying the presence of a particular analyte. It could be a small molecule, it could be a metabolite, it could be a peptide, it could be a protein, it could be an amino acid, and it has become extremely ubiquitous. It can be used for identifying, it can be used for quantifying. Two techniques, normal phase and reverse phase chromatography. The reverse phase makes use of a hydrophobic stationary phase and a hydrophilic continuous phase, and like water, acetonitrile, methanol. So reverse phase chromatographies have become extremely ubiquitous because the amount of solvent, the type of solvent which we use is very cheap. There are a plethora of detectors starting from UV, diode array, refractive index, electron light scattering, mass spectrometry detector, and so on. Depending upon the type of molecules you are trying to analyze, we need to go for different detectors. Then I talked about the concept of method validation, preparation of the standard graph, and how the method validation is extremely important, especially if you are developing it for the Food and Drug Administration or getting approvals for drug testing or approvals for clinical trials and so on. So HPLC is the most powerful tool which one makes use of, and it has become part and parcel of the research, the quality control, the analysis, the clinical trials and drug development and so on.